I'm Anil Kumar sharing with you a real test paper. Now this is chapter 6 Trigonometric Functions MHF4U. Day 2 they say. It seems this is a very important chapter and there are a lot of concepts to learn. And here is an interesting question to work on. So we are now trying to sketch reciprocal of a trigonometric function, right? So the question here is question number 6, which says graph the function f of x equals to half of cotangent 1 over 4x over minus 4 pi to 4 pi. Now we are given a graph paper here. I'm using the same test paper of my student, and well, it was a difficult test paper. Now let me show you how to really answer this question. So I'll draw the axis again so that we clearly have we can understand what's going on here. Okay, so this is our y-axis. Okay, and we are given the x-axis, which is kind of like this. We are also provided with the scale on this graph paper. So that's the y-axis, right? Now let us try to understand the strategy to solve such a question. It can be at times very difficult. F of x equals to half of cot 1 over 5x over a period of minus 4 pi to plus 4 pi. So if you have to sketch a reciprocal of tan, what you should do is you should start with tan 1 over 4x, right? So first thing we will sketch will be tan 1 over 4x, right? Now from here we'll get into reciprocal of tan, so we'll get cotangent 1 over 4x. You get the idea. And then we'll do half of it. Don't do the mistake of sketching half of tan 1 over 4x and then reciprocal of that. That will lead to error, right? So let us first sketch tan 1 over 4x. Now if the function is tan 1 over 4x, what is the time period? Now for tan, the time period is pi, not 2 pi. Do you understand? So when we are thinking about time period for tan function, it is how much? It is pi. It is pi, right? So when k is 1 over 4, in that case time period will be pi divided by 1 over 4. That is 4 pi. So 4 pi is the time period for tan. That is one of the reasons that this period is given to us between minus 4 pi to plus 4 pi. It is an educational test actually, and that is why I have taken up this as a video. Now, so let's get back to our graph paper. So here we are right at the origin, and we are given that the horizontal blocks are pi by 2 radians and the vertical blocks are 1 unit each. So let me make at least the vertical blocks clear. So these are 1 unit each, right? So 1 unit each, minus 1, minus 2, kind of like this. So let me write minus 1 here. And the horizontal are pi by 2. So on the right side, we have this as a pi. This is 2 pi, 3 pi, 4 pi. So this is 4 pi for us. Let me write with black ink itself. So we do have 4 pi written. Let me write it 4 pi. So that is one range. So here we have 2 pi. Okay, this is pi for us. Fine. 3 pi. On this side we have minus pi, minus 2 pi, minus 3 pi, and minus 4 pi. So we'll go up to this. That is our range. And then we have 1, 2, and so on the y-axis. Now we know the time period is 4 pi, and we also know that tan function is like sine, odd function, symmetric about the origin. So tan function really, this particular, when we say 4 pi, that means we can have a vertical asymptote for tan at 2 pi. So I'm drawing these lines. So we'll have tan function which will have vertical asymptotes at 2 pi, right? So basically the function will be kind of like this. Do you understand? I'm drawing a dotted line here at 4 pi, since half of tan will come along this line, right? These are my guidelines to help you how to sketch the cotangent function from the tan function. Okay, now since tan function will be kind of like this, it is an odd function, it is good to test or calculate the values on this quadrant, I mean from 0 to 2 pi, and then we can reflect them here and get their corresponding on between 0 to minus 2 pi. So that is a strategy I'm going to work with, right? So let's calculate the value of tan 1 over 4x for different values of pi, right? Or x, I should say, for x. So let's begin by writing x equals to, let's say 0. We'll start from 0 to 2 pi, right? So 0. So if in my calculator I plug in, so I'll use 1 over 4 as 0.25, right? So if I say tan 0.25 of 0 times 0 means 0, right? I'll get 0 as expected, so I get this value as 0. Now I will check the values at pi by 2, pi and 3 pi by 2 and also 2 pi, right? So I'll check values at pi by 2, then I'll check value at pi, 3 pi by 2 and at 2 pi. So these are the values I'm going to check. So we'll use tan. You can also do these calculations. 0.25 for 1 over 4, then we say pi, and then divide by 2 bracket close equals to 0.414. Now we will again do the same calculation, which is tan, within brackets we have to say 0.25 and this time pi, right? Pi bracket close equals to 1. Again tan, within brackets we have 0.25 times 3 pi by 2. So we'll do times 3 within bracket pi divided by 2 bracket close equals to 2.414. And then for 2 pi, so when I do tan 0.25 and I have to write 2 pi, so I'll do times 2 times shift pi bracket close. It gives you an error simply because it is infinitely large, so it goes to infinity, and that is why it gives you an error, right? So that is something which you need to understand. So based on this, I'm going to plot the points for tan 1 by 4x. So we get 0 here, perfect. And then at pi by 2, I get 0.41, which is less than 0.5. And at pi, I get a value of 1, so that is my 1. At 2 pi, I know it's approaching infinity. At 3 pi by 2, I have 2.41. So at 3 pi by 2, it is slightly less than. So these are my points. And you know, we have 5 points here. They're good enough to draw the tan function for us. Now since tan is an odd function, I could get these points here also. So that should be reflection, right? And then we have at 1, that is it, minus 1. And this will be minus 2.41, right? So minus 2, which is here, and 0.41 will be kind of here. You get it, right? So these are my points for tan of 1 over 4x. So let me just join them with a smooth curve, right? And we know this actually goes to infinity, like this. Remember, we have to do from minus 4 pi to 4 pi. Now this part will be positive and this part is going to be negative since tan repeats, right? So this same pattern is going to repeat. So at pi we have 1, so we can now write like this, and we kind of know our points to 2.4, so kind of like this, right? So here we get a graph which is kind of like this, right? So we are not continuing here. but we continue this side. Do you see that? Similarly, on this side also, it is going to repeat, right? So this value for this, we have 4 pi, correct? So at 4 pi, will have a 0, and again it is going to repeat. So we'll get a value here, 1, and then this will be 2.5. So we'll have we can draw like this. Now that is tan function, okay? So I'm just drawing an arrow. Perfect. So this is tan 1 over 4x, correct? So get to this point first and then do reciprocal of this function to get your cot 1 over 4x. Do you get the idea, right? So we will use another ink here, which I'm looking for. Which one? Okay, so let's use this blue. So now we will sketch cot 1 over 4x, right? So now we will sketch cot 1 over 4x, correct? That means reciprocal of this. Reciprocal means 0 reciprocal is in vertical asymptote, right? So x-intercepts will become vertical asymptotes for us. So that's my vertical asymptote for cotangent function. Do you see that? Okay. I'm purposely making it on the side so that you can at least see some part of it, right? So this is my vertical asymptote, and that one is for cot 1 over 4x, okay? So all these zeros of tan will get transformed to vertical asymptotes for cotangent. Perfect. The vertical asymptotes where the function is approaching infinity will become zeros. So these are my zeros, do you understand, for cotangent function. You get the idea. So these are my zeros for the cotangent function, right? So the vertical asymptotes which used to be there will become my zeros. So this is my 0. Reciprocal of positive will be positive, and 1 reciprocal is going to be 1. This is reciprocal of 2.4 is like 0.4 kind of here, and this point gets transformed to that point. Do you see that? So what I really get here is the cotangent graph, which is kind of like this. Do you see that? This is the graph which I get for my cotangent function. So it is going to be going through 1 and then here 2.4, right? So that is correct. 2.12 and 2.4 will be here. So this is my function for. So that is how it is going to be. I hope you get an idea. So this 0 is there. So this point will be at 1, right? And this point will come here. That point will go 0.4. So I have a function which is going to be like this. Going through the point of invariance, right? This points will get reflected. So this will be, this comes here and that goes there. So we have to go through this. So that is my cot of 1 over 4x. But what I need is f of x is half of that value. So I'll do one more step, and this time in black ink, and I'll say f of x for me is equals to half of cot 1 over 4x, okay? So each point will come half unit down, right? So for example here, this is at 2.4, so it will be 1.2. So 1.2 will be, so we are just pushing these points half value down. Do you see that? So this part, let me draw it neater here, will be kind of like this. So it becomes flatter. Do you see this? 1 will be at 0.5, right? So this point will be kind of here. So the graph will be kind of like this. So that is our final value for cotangent function. So from minus 4 pi to 0, it is going to look like this, and that is going to repeat. So we'll have here, this point will be here. So that is going to be kind of like this. Since there was already a graph here, so there's a lot of mess, but still I think you understand. Do you see that part? So That is our function f of x half of cot 1 over 4x. Now let me give you a complete picture of this. Let me move it slightly ahead. So we were trying to sketch f of 1 over 2 cot of 1 by 4x. The process is first sketch tan 1 over 4x over an interval of minus 4 pi to plus 4 pi. Then do reciprocal of that function to get cotangent 1 over 4x, and then vertically compress it by a factor of half to get the solution or the graph of f of x, which is equals to half of cot 1 over 4x over a period of minus 4 pi to plus 4 pi. I hope that helps. Thank you and have a good look.